Hello, this is Lance Levinson, and today we will be introducing the k-nearest neighbors algorithm, or simply the kNN algorithm. The algorithm is a machine learning method that can be used for classification and prediction. It is a very simple yet effective algorithm that has tremendous success in quantifying data for analysts to drive their data-based business decisions. It is often preferred because of its simplicity and lack of parametric assumptions. The idea behind the k-nearest neighbor method is to classify new data by identifying records in the training dataset that are similar to the new data. Like all classification methods, our goal is to make a good definition of the concept of similar. The way we do this for the kNN algorithm is by identifying the nearest k neighbors and classifying new data according to either a majority rule, a weighted average, or possibly another method. As you have probably guessed, we are once again tasked with defining what nearest means. While there are many ways to define the concept of distance, we will be using the Euclidean distance. Let's take a look at a business example to help us visualize what is going on. In this example, we will be using customer information at a bank to try to infer default rates on consumer loans. Let's take a look at a two-dimensional plot of the loan amount and loan duration for a subset of the data. We can't see much of a linear or curvilinear relationship between these two variables, so we know that none of our linear methods would be a good choice to model this data. But since we have a third categorical variable, we can differentiate the defaulted loans from the loans that are in good standing. So, if you received information for a new loan, what would be our best guess for its likelihood to result in default? It would be natural for us to look at the points around it and assume that the new record is of the same type. However, there are a few things that we should consider. For instance, should we use the nearest single point, the nearest 5 points, or the nearest 10 points? What if some of the nearest points are defaulted loans and some are healthy loans? Should we take a majority vote or some other method? Let's now take a look at more data points. One can quickly see that the clumps of defaulted loans are not as neatly defined. As you can see, the above questions now seem much more important since the data isn't so nicely clustered. We might actually get different predictions if we used a single neighbor, the nearest 5, or the nearest 10. How do we know which k gives us the best predictions? We begin our analysis by normalizing our data. It is very important to do this when using data that are on different scales so that the differences in each will be directly comparable. If we fail to do this, the measurement with the larger scale will have a much greater effect on the distance calculation. For instance, without normalizing our data, a difference between a loan with a 2-year duration and one with a 3-year duration would be 50,000 times less than the difference between a loan with a value of $100,000 and that of $150,000. Since the kNN algorithm relies heavily on the concept of difference, we need to normalize our data to the same scale. So, how do we find the best value for our model? Well, we need to calibrate our model with the known data. We begin by partitioning our dataset into training data and test data. We will test the test data against the training data and try to minimize the number of incorrect predictions. We can then use this model for new unclassified data. Let's take a look at the error rates for various values of k. As you can see, using our test set yields an optimal result of 20 for k. We will be using the class package in R, which has an implementation of the kNN algorithm using Euclidean distance as the measure of nearest. If we look at the function call, we can see that the parameters are laid out as follows. Train is the training dataset that we will be using to calibrate the model. Test is the test dataset we will be minimizing the errors from. CL is the actual classification of the test dataset. K is the number of neighbors considered. L is how we would like to assign classification if there is a tie between the nearest neighbors. Choosing a higher value of k will provide a smoothing effect that will reduce the likelihood of overfitting. However, if k is too low, we may find that we are fitting the model to the noise. Finding the right balance is more of an art than a science and depends greatly on the nature of the data. Typically, k falls in the range of 1 to 20, with odd numbers being used to avoid ties. How about visual representations of the data? We can show plots of the data set and separate the defaulted loans according to the point type. We can also show the predicted values on our plot using our new kNN model. In our example, we have illustrated how to classify a new categorical record, but the kNN algorithm may also be used to predict a numerical response. The process is very similar, however, instead of taking a majority vote as to the category of the new record, we take an average of the nearest k numerical responses for our numerical prediction. This is often a weighted average, giving the nearest k neighbors higher weights. Rather than the error rate that we used in the kNN classification example, root mean square error is used in numerical prediction. An example of how we can use the kNN algorithm for a numerical response would follow directly from what we learned in our linear regression session. Instead of minimizing the sum of squares of the distance between the points and the predicted value, we can use the kNN algorithm for our predicted values. As you can see, in certain instances, the performance of the kNN regression is superior to that of ordinary least squares, especially when the data is nonlinear. So, what are some things we need to keep in mind when using this algorithm? When we use numerical predictor variables, we need to make sure that we standardize them to equalize the scales. If we fail to do this, the measurement with the larger scale will have a much greater effect on the distance calculation. A drawback of the basic majority voting classification of the k-nearest neighbor algorithm is that classes with outcomes that are more frequent will tend to dominate the classification of the record. Because of the sheer amount of them, they tend to dominate the calculations. As previously discussed, the kNN algorithm is somewhat sensitive to the local structure of the data, and the accuracy of the prediction is affected by noisy features. Larger values of k reduce the noise, but the smoothing effect makes the boundaries less distinct. Lastly, the computation time for the algorithm is relatively expensive since we need to calculate so many distances. The number of records required in the training set to qualify as large increases exponentially with the number of predictors. As we have seen, the kNN algorithm is a very powerful algorithm for business analytics and often has superior results and lower error rates than many other popular classification and prediction methods. It is relatively simple to implement and is not very computationally expensive, making it a favorite for business analytics.